Where we left off yesterday was the second step of the DC3 algorithm, where we induced the relative order of the suffixes that start at a multiple of 3 from the ranks that we recursively computed, namely those blue ones, the suffixes that don't start at a multiple of 3. What is left to do is merging these two things. We have a sorted list of suffixes, all of those that start at multiple of 3, and we have a sorted list of all those that start at other positions. And I showed these here in green and blue. And so these are sorted lists of strings, and we would like to merge them. And the approach will be to use the standard merge sort merge method. So we start at the beginning. The first overall suffix must be one of the first of these two, so we have to compare them. And then the smaller of the two gets output, and we move to the next one. So in this case, the first one will be this $, because we always assume if nothing comes, then this is sorted before anything that has another character. So I've done this with a few of the first suffixes to show how we get going in the general case. So here you see these are alphabetically sorted, and I stopped at a certain point, namely at these two. So the next step, we know these, we have the first two green ones and the first 3 blue ones. These are the next 2 suffixes that we have to compare. Now we'd like to know which one is earlier in the alphabet. We could just compare them character by character, but that's too slow. We only have a constant time in our performance budget. So we have to do this really, really quick. Now we've already seen a trick just yesterday in step 2, how we can sometimes do this comparison very quickly by chopping off the first character. So let's try the same trick. Here's our green string. If we take the first character off, we are guaranteed to land in the blue set. And we also know which of the suffixes that is, because it's exactly the one that starts one character later. So that's easy. We can do the same thing with the blue string. We chop the first character off, and then, oops, we're ending up in the green set again. So we know which one it is, but we are still comparing one green and one blue, an apple and an orange. So we still don't know which of the two comes earlier in the alphabet without spending more effort. So it seems not to work in this case. But don't you worry, it is just another step that we need to make, and then it always works. And that is just because of the fact that we have every third in this list. So you occasionally get this case that chopping off one character, you're still both in different sets. But if you then do it another step, so right, what you do is you take one character off, and you do this with another one that is positioned somewhere else. I wanted to make this a little longer. So here are 2 suffixes. So sorry, they should really stop at the same point. And you're trying to get them both into the greens, into the blue set. And the blue set has 2 out of 3 positions. Maybe these 2, and then there's one green one. So here's 1 green position, 2 blue positions. Every position is either green or blue. And now, of course, these are colored in the same way. Now, originally, this one starts green, this one starts blue, so they're in different classes. If you chop off the first character here, they're still in different classes, now opposite. But if you also chop off this character, you're guaranteed that they're both in the blue set. And you can think about this. You always have one of the 2 cases. Either you have to chop off one character and they're both in the blue set, or you have to chop off 2 characters and then they're both in the blue set. but it always is just at most 2 characters that you have to take away from these strings. And then you end up in a situation where you have 2 blue ranks, 2 blue suffixes whose ranks you know, so you can compare them. Okay? That's an important, that's the key step for the merging. So let me know if this step is clear now. If you have questions, as always, put them in the Q&A. So we need just constant time for this comparison, because what we do is we, instead of originally comparing 2 suffixes, we now compare 1 or 2 pairs of letters, chopping off the first characters. Only if they are equal, we have to continue. And in the worst case, we have to find the first 2 characters of the 2 suffixes are the same, the second characters are the same, and then what remains is 2 blue suffixes. So we look up using R their rank, and we compare the ranks as numbers, and then we know the outcome of the comparison. It cannot come out equal. That's because we have the end of word marker. So we will always find in at most 3 steps which of the 2 is smaller, and then we can put this next one, which is it in this case, 17 and 13. So 17's here, 13's here. So 13 would be the one. So the green one should be the next one that comes here, which sounds wrong. No, it's the other one. The 11 is this one. So the blue one is the next one, of course. So the next entry here would be T11, copying whatever that string is. That way we can get in constant time the next entry. So we produce the sorted list of suffixes in constant time. And that concludes how to do the overall 3rd step of the DC3 algorithm in constant time, in linear time. Okay. This is almost it. Unfortunately, there's 1 or 2 caveats with this. So we've shown that both the inducing the ranks for R3 is linear time and the merging is linear time. But if you look closely, we actually cheated in the step 1. I simply said step 1 was recursively sort the suffixes that start at different positions, not a multiple of 3. Compute this R12 recursively. But it's not really an instance of the same problem, because to call this recursively, we would need a single string so that these are the suffixes of this string. That's the problem that we're solving with the main algorithm. That's the problem that we can recurse on. But what we now have is a weird set of strings. It's, well, 2 out of every 3 suffixes of a given string. How can we even apply the method to this? For that, we have to look a little closer. And it seems that this doesn't really work. But you can make it work with a trick. I'll move out of the way for the example in a second, but let me first discuss this. The key insight is we don't directly use the same text. We modify the text in 2 ways. First of all, we don't consider the original alphabet, but we make new compound characters that each consist of 3 of the original characters. And I'll denote these by these little boxes. Now, if you take, so this is where the example is important. Here's our original text, banana ban, and we fill up with dollars as convenient. And then I'll denote with tbox, the boxed string, where you just take triples and make 1 character out of these. If you take the suffixes of this tboxed, then these are exactly the original suffixes that start at a multiple of 3. Because the suffixes of this thing, they start with everything, and then the next thing leaves out the first 3 characters. The first 3 characters, the first 6 characters omitted, and so on. Okay. So I hope that's the easy part. We can emulate this skipping suffixes by grouping characters together and making these boxes around them. So instead of the alphabet B, A, N, and $, we now have the alphabet of ban, of Anna, of another ban, of $, and all the other triples that might occur in your text. So this would be fine for recursing on all those. We want to recurse on all others, so you have to apply a slight additional trick. And the trick is this. Instead of the original text, you generate this weird text where you take the suffix of t, where you start at the first position, and take the box version of that. So that would give you T1 and T4 and T7 and so on. All the ones that are 1 modulo 3. And then you append another copy of T where you start with the second character. So from this you get T2, T5, T8, and so on. And you insert $ triples in the middle so that you can separate those two. Okay, so that means even though suffixes of this text, they're either starting with something here or they're starting something with here, and there will always be a $, so that for those ones that start here, they have this long tail of the entire copy of the text, but we can ignore that because we know once we see the $, we can actually stop comparing. Okay, so we recursively compute the suffix array, the inverse suffix array, rank array, and leaf array on this T prime. And if you check, the math works out. We took 2 copies of T, but we grouped triples of characters. So that still has roughly 2/3 n characters now. So it's the same reduction in the input size. And now the problem fits the original description, and we can recursively call the very same algorithm on this. That's brilliant. Now, because of this fix, we actually created a new problem. And to illustrate the problem, you have to really look carefully. So this is something that's very easy to overlook when you first think about it. So this seems to work fine, right? We know how to do step 2 and step 3, and we know how to do step 1, and we have reduced it in a way to compute suffix and rank and leaf array on another string. So where should there be a problem in this? Maybe you can think about it and throw it in the Q&A. This would be a good time to pause the video if you're watching this offline. But because we have some more material for today on the list, I want to go on and just tell you what happens. So what obviously happens because we take triples is that our alphabet cubes in every recursive call. Right? We start with sigma characters. That's the original string, and that can be any number, but you can assume that sigma is at most n because it doesn't make much sense to have an alphabet with more characters than ever occur in your text. You could always reduce that to the characters that are only the characters that occur in your text. But then in the first recursive call, we make triples out of that, and they're sigma cubed triples of 3 letters from this alphabet. The next recursive call, we would take sigma cubed and cube that again. That's sigma to the 9. And you keep doing this. So even if originally sigma was 2, just a binary alphabet, after 10 steps you have 1,000. Cubed, so whatever that is. What's 2 to the 30? That's already in the billions. That's almost the capacity of an int, and that's 4 billion. So it's roughly 1 billion. So that's already really bad, and that's just 10 recursive calls. You will need a few more if your text is long. So this will completely explode. Your alphabet will be big. Now, that is not by itself a problem, but we relied implicitly on this linear time sorting. Let me just briefly go back to that step to make this very clear. We rely on linear size alphabets in this step. We induce the ranks in step 2 from the ranks that we recursively compute by replacing the long suffixes by these pairs, a character and the rank from the remaining suffix. The rank is fine. That's always a number between, I don't know, 0 and n. But the first here is one character from our alphabet. And if the alphabet explodes, becomes bigger and bigger, then this becomes much longer, and we cannot do this linear time sorting anymore, because that only works if we're sorting something where the range is roughly as big as the list we're sorting. Okay? I hope the problem is clear now. So this is the problem. What's the solution for this? The solution is to observe that, yes, the alphabet can become very big, but there's no way we can use all these different triples in each step. Remember, our t prime, the text that we recurse on, it only has 2/3 n different characters. That's the length of this text. So that can be at most that many different triples that are actually occurring in our text. So what we do is an alphabet reduction, a step where we replace the actual triples by a number, or by a different alphabet if you want, but it's convenient to think of these as numbers. So what we do is we take all the triples that actually occur, make a list of these, and then we sort them. This can be done in linear time because in the initial step, sigma is say a constant or even bounded by n, it's order n. So we have triples of numbers that are each from order n. So 3 steps, radix sort with 3 steps, or 3 rounds of counting sort, same thing, can sort any list of such triples. That can be done in linear time. And then we have a sorted list of these triples, and we replace every triple by its rank. I'll have an example on the next slide. So that ensures that in all recursive calls, we always have an alphabet that's at most as big as the text is long. That's always sufficient. It always makes sense. But we need this extra step because we computed the text over a very large alphabet. So we have to do this alphabet reduction step in between. So as promised, here's an example for that. Here's our my favorite example from this subsection where we need a little bit longer text, Hannah Bends Bananas Man. And so here's the T prime. Here you see T1, it omits the first character. T2 omits the first 2 characters. And then you just, well, you fill up with dollars here in the text whenever you need it. So you just fill that up with dollars so that it aligns with multiples of 3. That's easy to do if you actually compute the triples. So here's T prime, how it actually looks. It has lots of these triples, but that's way fewer than, what's the alphabet size? We have H, A, N, B, S, M. So maybe six different characters if I can count. 6 to the power of 3 is already, I don't know, a big number. Something like almost 200. There's definitely not 200 different triples that occur here. The occurring triples are actually these. There's Anna, that's occurring twice, and the dollar, that's occurring twice. There's not many duplicates here, but there's many triples that don't occur here, like triple S or triple N or whatever else. Right? Then you sort those triples that occur, 3 rounds of counting sort. Then you get the ranks of these. And finally, you take every triple and replace it by its rank. So just do this in slow-mo. If you have the triple A and N, you find that in the list. And the way to do this is you probably want to do some hashing trick in this to implement this mapping efficiently, but let's omit that detail. So suppose you have a way to quickly find, we didn't talk about hashing in this module. Suppose you have an efficient way to find, oh, we can just use a trie, a depth 3 trie. Okay, you insert all these into a trie and store the rank there. So in constant time, because it's just depth 3, you can find this. And so you replace this by its rank 3. Let's do another example. AHB in the sorted list is here. So you replace it by its rank, etc. You will also notice that the triple dollar necessarily is the first character in the new alphabet because it comes before all the other triples. So this will always get a rank of 0. And so we'll serve the role of a new dollar character in the reduction. Okay? That's how you get the T double prime, which is the actual string that you do the recursive call on, where you can say the alphabet is bounded in size in the length of the string. But that is really it. That's all there is to the DC3 algorithm. So the steps are, first, you do the recursive call. For this, you construct T prime as shown here. Then you sort the triples and reduce them to the rank. That gives you T double prime. On that, you really recurse. When you come back, you have computed the R12, the ranks of all the suffixes of this string, which can be mapped back to the suffixes of T that start at not the multiples of 3 positions. From that, you induce the ranks of all the suffixes that start at multiples of 3. And then you do the merging step. And both step 2 and step 3, again, use the tricks I've shown before to run in linear time. That's how you construct a suffix array in linear time. No matter how big the alphabet, no matter what the string looks like. This is worst case, always works. The algorithm is a bit complicated because of the different steps you have to combine, but each of the individual steps is not very hard to do. And you can implement this in fairly concise code also. The paper that presented this algorithm has an implementation in the paper that fits in the appendix. So this is fairly efficient in practice and close to the methods that are used. There are further tweaks to make it slightly more efficient, but that's the core method that's behind these. So that brings me to the end of the suffix array section. We've seen that compared with the suffix tree that has all these pointers and the worries how to represent a trie in memory, etc., in a memory efficient way, the suffix array is just an array of numbers, and that's very easy to work with. And space efficient as well. It's very simple to construct it on random strings. I just want to add this here again. So this is the fat pivot radix quicksort, which is working very well if you just apply it to usual text. But the guarantee is much weaker than this in the worst case. But we've also seen we can do it in optimal linear time up to a constant factor at the same time as you need to read the text. And unlike for the suffix tree algorithms that were known before that, this is actually with a reasonable constant. You can do this on really large strings. And the suffix array in isolation is already enough to support efficient string matching. We've seen that at the very beginning. You have a sorted list of strings, so you just use binary search. That is already pretty good. You can speed up that search a little bit. That's something we didn't talk about, but we'll get to something that's better than this anyway. So a slight downside in the pure form, like I've shown it. String matching takes m times log n, not the optimal order m time. But even if the text is very big, log n is not unreasonable. The more important downside is, as it stands, the suffix tree had all these applications. Remember, I listed 6 applications, and Gusfield's book has over 20. The simplest one might have been string matching or pattern matching, but there's many others, and it seems for those we can't easily use suffix arrays. So there's still something to add to make them as versatile and powerful as suffix trees, and that's what we will actually look at next.